Welcome back. I should mention that at the end of the last video, I said that very often in using the mean value theorem, in practice, it's going to be most helpful when we need to know that a point with a certain property exists. So like Maud was speeding at some point, so therefore she has to pay the speeding ticket, without necessarily having enough information to know exactly when that happened. The toll booth collector did not know a precise moment that she was speeding, just that such a moment existed. Now, there aren't a whole lot of scenarios where we're going to find ourselves in that situation where we need to know that there is a point with this property without being able to find that point. Those of you in the honors section will see a little bit of that in the next honors worksheet. Okay. All right. Now, section 4.2, which is the section we're in, is sort of a standalone section. There are a bunch of important theorems in calculus, and it puts a bunch of them into here. So the next theorem is Rolle's theorem. It's actually a special case of the mean value theorem. So it states this: if f of x is continuous on the closed interval from a to b, and f of x is differentiable on the open interval from a to b. These two hypotheses are exactly the hypotheses of the mean value theorem. Seems like I'm stating that, except that I'm going to require one additional condition. I'm going to require that f of a be equal to f of b. And so I want to see if we can figure out what our conclusion is. So let's think about this. Here's some point A and here's some point B. And what I know is that the heights of my function are the same at that point. That's what this third condition says. The first two hypotheses just say I've got something that's continuous and differentiable, so I know the mean value theorem applies. But that's interesting, because if I look at the secant line, if it's through 2 points at the same height, it's a horizontal line. So there's got to exist some point where the tangent line is horizontal. And that's what our conclusion is going to be. It's just making it more specific to account for this. So then there is an x value c. Again, it has to be in the interval from a to b such that f prime of c is equal to 0. And you might say, well, why do we need Rolle's theorem if we have the mean value theorem? The reason we need Rolle's theorem is because it's actually easier to prove Rolle's theorem than the mean value theorem, because it's the special case. But once we know that Rolle's theorem is true, it makes it easier to actually prove the mean value theorem. Now, given that we're meeting by video and that's already kind of tricky and taxing on all of us, I'm not actually going to work through the proof of the mean value theorem. If any of you are curious about it, I'm more than happy to work through it with people individually. We can do that in office hours or by appointment. Just let me know. I'm certainly happy to show that to you, but I'm not going to lecture on it in these videos. So I'm just going to state it, and that's why we need that, is that sometimes it's easier to prove a small case and then sort of bootstrap yourself up to the general case. So if we were proving this, we would prove Rolle's theorem and then use it to prove the mean value theorem. Okay. All right. Two other theorems that we have in this section that don't have fancy names like this. They're just Theorem 5 and Theorem 7. Let's see. And Theorem 5 says, I want to make sure I state it exactly right, yes. If, this is Theorem 5, if f prime of x is equal to 0 for all x in the interval from a to b, then f of x is constant on the interval from a to b. Yes. I was just checking my notes, because if we threw in the additional hypothesis that it was continuous at these endpoints, it would actually be constant on the closed interval. But this book statement of this theorem does not throw in that additional hypothesis. Not super earth-shattering, okay? This just says, okay, if you've got a horizontal tangent everywhere on an interval, you're talking about a horizontal line. You've got a constant function on that interval. Okay. Theorem 7 is a corollary of this. Okay. And it says this: if f prime of x equals g prime of x on the interval from a to b. So if I have two functions whose derivatives are the same. Now notice, if their derivatives are the same, then if I subtract this over, the derivative of f prime minus g prime, which is just the derivative of f minus g, would be 0. So they're saying that then f of x minus g of x is constant on AB. Or an equivalent way of saying that is equivalently f of x is equal to g of x plus some constant. That way, if I subtracted over the g of x, I'd get that the difference was constant. Okay. This is actually going to be incredibly important. The derivatives of functions describe the behavior of the functions. Makes sense that if two functions have the same behavior, there should be a pretty strong connection between them. And this tells us what that connection is. If I have one function and I have another function with the same derivative, it's just going to be a vertical translation of the original function. I can move it up or down. That's what adding a number c does. But I can't change it in any other way, or that would change the derivative. So this is going to be a super important theorem for us as we move on later on through the semester. All right, there we go. And I can turn off the video.